Welcome to this explainer. If you're in high-end manufacturing, automotive OEM, or heavy-duty infrastructure, you already know a coating isn't just paint, right? It's a highly engineered protective shield standing between multi-million-dollar assets and, well, absolute ruin. Today, we're going to unpack a sleek, modern industrial blueprint together. We'll be breaking down the 6 major coating resin families that completely dominate the global market. Think of it as a fascinating look at molecular architecture, how we translate raw chemistry into high-performance, real-world solutions.
So, let's jump right in with a question that honestly traps a lot of novice formulators. Is there one perfect, universal coating for every single industrial job? I'll save you the suspense. Absolutely not. We call this the coating resin paradox. Every single chemical advantage you gain brings an equal and opposite constraint. The real magic of industrial formulation isn't about finding some flawless, mythical material. It's about selecting the right molecular flaws to tolerate based on your exact application. To master this, we have to understand the fundamental DNA of the Big Six.
Okay, let's dive right into this. We're starting with the undisputed heavyweight champion of the heavy-duty world, epoxy resin. The core of epoxy's power comes down to its chemical structure, specifically this highly reactive 3-membered epoxy ring. This isn't just a physical barrier we're talking about, it's a chemical anchor. When epoxy cures, usually with an amine hardener, it creates this densely cross-linked, incredibly stable matrix. It really is the standard for foundational industrial protection.
Just look at these extreme capabilities. Epoxy's adhesion is simply unmatched. Up to a 15 megapascal grip on steel. It literally anchors itself into the metal's microstructure. Plus, you get practically zero volume shrinkage, so you can apply massive, thick coats in a single pass. Sounds perfect, right? But here's its fatal flaw. Epoxy is essentially a vampire in sunlight. It has almost zero UV resistance. If you leave a pure epoxy coating outdoors, the sun's energy will completely shatter its molecular chains, causing it to yellow and chalk in under 6 months. That's exactly why epoxy is strictly confined to indoor use or buried as an unexposed base primer.
Which brings us perfectly to family number 2. Polyurethane, or PU. Now, if epoxy is your rigid, unyielding anchor, PU is the ultimate shock absorber. Its secret sauce is this microphase separated structure. Polyurethane molecules naturally arrange themselves into alternating hard and soft segments. The hard segments lock together, acting almost like built-in nano-reinforcements, while the soft segments give you continuous flexibility. This means PU delivers extreme mechanical versatility. It endures impacts and bending without shattering.
But, not all PUs are created equal. The showdown between the 2 main types is really interesting. On one hand, you've got aromatic PU, made from TDI or MDI. It's highly reactive, great on the budget, but its chemical ring structure soaks up UV light like a sponge. It'll yellow super fast, making it an indoor-only player. On the other hand, we have aliphatic PU. Structurally, it literally cannot absorb UV light. It is chemically blind to the sun. Sure, it costs more, but it yields zero yellowing, making it the ultimate B2B sunscreen. If you're engineering a top coat over an epoxy primer for an outdoor bridge, aliphatic PU is your only serious answer.
Moving on to resin number 3, acrylic resin. Think of this one as the modular chameleon of the coatings world. It's built on a highly stable carbon-carbon main chain that refuses to easily degrade. But the actual magic, it's in how formulators put it together. By mixing and matching different monomers, hard ones for scratch resistance, soft ones for flexibility, and functional ones to allow for chemical bonding, engineers can dial in the exact glass transition temperature, or TG, they need.
Acrylic really is the ultimate flexible partner. You can formulate it as a thermoplastic for super fast physical drying, though fair warning, you'll sacrifice solvent resistance. Or you can make it waterborne for low VOC, eco-friendly jobs. You can even make it thermosetting. But here is the catch, its fatal flaw. On its own, it rarely achieves peak industrial performance. To get extreme, heavy-duty durability, thermosetting acrylics absolutely must be paired with an external crosslinker. It's the ultimate team player, perfectly designed to combine with polyurethane or our next industrial resin.
All right, let's shift gears and talk about the classics. Number 4 is alkyd resin. This is honestly the oldest workhorse in the industry. Basically, a polyester resin tweaked with plant oils and fatty acids. And what makes alkyds so cool is how they cure. They don't rely on chemical hardeners being mixed in at the very last second. Instead, it cures automatically through an oxidative chain reaction the literal second it touches ambient oxygen.
Because it just needs air to cure, alkyd is the absolute DIY champion. It's a true single component or 1K system. pop the lid, brush it on, and you're done. That ridiculously low application barrier is exactly why it still dominates architectural paints and basic consumer maintenance. But its market share in high-end B2B applications, it's shrinking. Why? The fatal flaw again. Its adhesion and weatherability are strictly average, and it has absolutely terrible resistance to high heat and alkaline environments, like fresh concrete. It's incredibly convenient, for sure, but it's not exactly bulletproof.
So the crucial point is, what happens when you actually need bulletproof? Well, that's where amino resin steps onto the field. Now, amino is a bit of an outlier on our list because it is not a standalone coating. It literally cannot form a film by itself. Instead, amino, specifically modern variants like HMM, is an industrial baking crosslinker. Remember earlier when we said acrylic needs a heavy-hitting partner for peak performance? Amino is that heavy-hitting partner.
Amino is pure OEM muscle. When you mix it with an acrylic or polyester, it unlocks massive cross-linking density. We're talking unbelievable hardness, chemical resistance, and that mirror-like high gloss you see on cars. This is the exact formula that dominates automotive manufacturing lines and metal coil coatings. But its flaws are rigid, literally. It's extremely brittle without a softer resin to balance it out, and it strictly demands industrial ovens running at 130 to 150 degrees Celsius just to cure. You simply cannot use amino resins for a quick field repair. It is exclusively a factory flow powerhouse.
All right, finally we reach the absolute extremes. Resin number 6, silicone resin. While the first 5 resins rely on carbon chains, which, let's face it, eventually burn and disintegrate under extreme heat, silicone completely swaps carbon for a resilient silicone-oxygen backbone. It's essentially the chemistry of quartz and sand. It is the undisputed high-heat hero of the industrial world.
Just look at this staggering leap in temperature tolerance. I mean, alkyd taps out around 120 degrees Celsius. Even our heavyweight epoxy starts breaking down at 150. But silicone, it sits comfortably at 600 degrees Celsius, long term. And what's truly mind-blowing is how it behaves as it heats up. Traditional resins melt or turn to ash. Silicone actually undergoes further condensation at high heat. It doesn't degrade, it actually gets harder and more densely cross-linked the hotter it gets. No way around it, that is just cool chemistry.
But as you've probably guessed by now, our high-heat hero has a pretty major Achilles heel. Yes, it survives 600 degrees and can brush off UV rays for decades, but its ultra-low surface energy gives it absolutely terrible natural adhesion. It struggles to stick to bare steel unless you use specialized silane coupling agents acting as a chemical bridge. On top of that, to fully cross-link, it demands massive baking temperatures, upwards of 250 degrees Celsius. It's an incredible material for sure, but highly restricted by these extreme application constraints.
And this brilliantly illustrates how the real magic happens out in the field. Senior engineers don't just pick one resin off a shelf, they architect complete systems. Got heavy-duty outdoor steel? You're laying down epoxy for that 15 MPa grip, and then topping it with aliphatic PU to shield it from the UV rays. Automotive OEM? You pair acrylic and amino, bake it at 140 degrees for 15 minutes, and hit a stunning 90+ gloss. Extreme heat exhaust stacks? You deploy silicone, surviving past 300 degrees where any carbon-based paint would literally vaporize into ash.
Which brings us to the real mindset shift you should take away from this explainer. The key realization is this. Senior engineers don't look for flawless materials. They engineer the perfect balance of constraints. There is an eternal, fundamental thermodynamic trade-off between cross-link density, which gives you chemical resistance and hardness, and flexibility. You cannot have maximum hardness and maximum shock absorption in a single molecule. High performance always demands high application limits, whether that's intense oven heat or incredibly precise chemical mixing.
You have to design your solutions around the messy boundaries of the real world. So as we wrap up this explainer and this deep dive into molecular architecture, I want to leave you with one final thought. Look at your own operations. What specific constraints, whether that's extreme heat, UV exposure, mechanical flexibility, or just a really tough application environment, are you trying to balance in your next project? Because once you understand the DNA of these 6 resins, you're no longer just painting, you are engineering a shield. Thanks for joining me on this explainer, and I'll catch you in the next one.